Hello students, in last lecture we discussed about the design step of post-tensioned two-way pre-stressed concrete slab, and in today's lecture we are going to solve the numerical on the design of pre-stressed concrete two-way slab. So here is the numerical statement. Design a post-tension pre-stressed concrete two-way slab 6 meter by 9 meter with discontinuous edges of support and impulse load of 3 kN per meter square. Cables of 4 wires of 5 diameter carrying an effective force of 100 kilonewtons are available for the use. Design the spacings of the cable in the two directions and check for the shape of the slab against collapse and excessive deflection at service loads. Assume FCK is equal to 40 Newton per mm square and Fp is equal to 1600 Newton per mm square and AC is equal to 38 kilonewton per meter square mm square. The grade of concrete, yes, already we have considered it has FCK is equal to 40 Newton per mm square. So this is what the numerical statement we have, and we'll solve this numerical by using the steps which we have seen in the last lecture. So let's start. So the very first step to begin with is the identification of the type of slab. So the dimension of the slab is given. Lx is equal to 6 meter, Ly is equal to 9 meters. So the ratio of Ly by Lx is equal to 9 by 6 is equal to 1.5, which is less than 2. So we can say that the given slab is the two-way slab. So for the identification of the two-way slab, basically we have two conditions. One is the Ly by Lx ratio, and second is the supporting condition. If a particular panel is supported on all the sides, all periphery, and if the Ly by Lx ratio is less than 2, then we can say that the given slab is. Now the step 2 is to find out the thickness of the slab. So to get the thickness of a two-way slab, we have the empirical formula, smaller span divided by 50. So here the smaller span Lx is given as a 6 meter, and if we divide it by 50, then we'll get, if we do that calculation, then we'll get the answer as 0.12 meters. Means the thickness of slab, whatever we get from this equation, is 120 mm. Okay, so this is what the step 2. Now the step 3 is the load calculations. So here in this for this particular numerical, we are going to focus on dead load and live load. For dead load, we are going to calculate the self weight of the slab, and we are going to consider the floor finishes, and we assumed the live load is given for this numerical as 3 kilonewton per meter square. So first of all, let's calculate the self weight of the slab. So how we are going to calculate the self weight? Self weight is nothing but the total thickness of the slab into density for the unit area. Okay, so 0.12 into 24 into 1, that will gives us 2.88 kilonewton per meter square is the self weight. Live load is directly given 3 kilonewton per meter square, and we assume the floor finishes as 0.12 kilonewton per meter square. And all together, if we consider all the loads, then the total service load whatever we get is nothing but, if we do that calculations, the addition of 2.88 plus 3 plus 0.12 is 6 kilonewton per meter square. Again, if we want to calculate the ultimate load, because in the given numerical we are going to take the various checks for this particular slab. So for that we require this ultimate load. So partial safety factor, we are going partial safety factor 1.5, we are going to multiply it by W, so we get the ultimate load as 9 kilonewton per meter square. So in this way we are going to calculate the loads, dead load and live load. Dead load is the addition of self weight and floor finishes. Live load is 3 kilonewton per meter square. Also we have calculated the ultimate load for the given numerical. Now let's move towards the next step, that is step number 4. So step 4 is what? Working moment in the middle strips are given by the table 26. Means in step number 4 we are going to do the analysis of the given slab, given two-way prestressed slab. And in this analysis we are going to calculate the moment in x direction as well as in the y direction by following the IS code clause. Table 26, is there to get the values of moment coefficient alpha x and alpha y. I have taken this screenshot from the IS code clause D1.1, the maximum bending moment per unit width in the slab. So this formula is for the per unit moment, okay, mx and my, but here in this step number 4 we are going to calculate both per unit moments as well as the total moment in the particular span. So let's see here, these diagrams are given in the IS code, figure number 25A for the span Lx and 25B for the span Ly. So if we observe this figure, the entire span is divided into the number of strips, edge strip, middle strip, edge strip, and the same thing is done for the span Lx and span Ly. So we need to remember that if we are doing the calculations for the span Lx, we are going to consider the middle strip length as 3/4 of Ly, and if we do the moment calculation for the span Ly, we need to consider the length of middle strip as 3/4 of Lx. Means vice versa relation is there. Okay, so we have the values of Lx and Ly, so we can get the middle strip length also with the help of this figure. And table 26 of IS 456 2000 is going to give the values of coefficients of moment alpha x and alpha y. So how we get that alpha x and alpha y value? So here is the screenshot taken from the IS code, table 26. So first of all, we get the values of alpha x and alpha y by using the support condition. So for this given numerical, it is said that all edges are discontinuous. So for all four edges are discontinuous, means this is the case number 9 of table 26. And according to the span ratios Ly by Lx, so we have Ly by Lx ratio as 1.5. So for this 1.5 ratio, we have the value of alpha x as 0.089, and for this 1.5 same span ratio, the alpha y value is 0.056. Okay, so here is the summary of that. Ly by Lx is 1.5, the value of alpha x 0.089 and alpha y 0.056 from the table 26 of IS code, IS 456 2000. Got it? So this simply we need to take that ratio, and for that ratio we need to check the given support condition. Then we'll get the values of alpha x and alpha y. Clear? Now once we get the values of alpha x and alpha y, we are going to calculate the moments, moment. Okay, so this is the formula in the IS code. Mx is nothing but alpha x w Lx square. Now again question may arise this in your mind, why we are not using the wu over here, only w, why we are going to taking the value of w? Because in the given numerical it is said that check the given slab for the serviceability condition, and for limit state of service the value of w, we are not going to multiply it by 1.5, so that's why we have taken the value as w only. Okay, now the alpha x value is there from table 26, 0.89. W is nothing but the 6 kilonewton per meter square, and Lx means shorter span is a 6 square. If we do the calculations, we get the answer as 19.3 kilonewton meter per unit width. So this is the moment for unit width. In the same way, do the calculations for my, but do remember that in IS code also it is given that we consider the LX span for my moment. Okay, for mx moment we have considered the shorter span, and for my moment also we have considered the shorter span. So this is the most important thing we need to remember while designing. Okay, so the if we do that calculation, then we'll get the value of moment is 12.1 kilonewton per unit width. But we want but for the actual design we want the total moment in the middle strip. So to get the total moment in the middle strip, what we need to do is we are going to multiply this moment per unit width by middle strip length. So the middle strip length, first of all we are going to calculate. So middle strip length in x direction is 3/4 of Ly, means 3/4 of 9, and that answer is 6.75 meter. And middle strip length in y direction is 3/4 of 6, that is 4.5 meter. So this middle strip length now we have. Now we are going to multiply 19.3 and 6.75, that will give us the total moment in the middle strip in x direction. So that answer is 130.275 kilonewton meter. So this is all the total moment. In the same way we are going to do for the y direction. So for y direction, the value of moment per unit width is 12.1, and the strip length, middle strip length in y direction is 4.5 meter. And after doing the calculation, we get that total moment as 54.45 kilonewton meter. Now we have total moments in x as well as in y direction. So this is what the analysis part. Okay, now after getting the moments, total moments, so we by using this moment we are going to find out the prestressing force. Okay, so step number 5 is to finding out the prestressing force in x direction. So how we are going to get that prestressing force? So for this force calculation, we are going to follow the basic principle of stress diagram for type 1 service condition. In that we have seen that triangular shape stress diagram we have, and the basic formula for the stress is moment, sorry, actually stress diagram, and from that stress diagram we have the total resultant forces, total compressive force we have, total tensile force we have, and the lever arm we have. So the moment which we are getting from that stress diagram is force into lever arm is nothing but the moment. Okay, so see here the formula I have means this is the same formula. So force is equal to moment divided by distance. In this way we'll get that force. But to find out the distance between the top kern and center of the cable, we need to add kern zone plus E. And for rectangular section, do remember this thing. For rectangular section, the kern zone is h by 6. So derivation already we derived in the previous lectures. Okay, on the Google Classroom, on the Google Meet, we derived that expression h by 6. How that h by 6 come for rectangular section? So h by 6 is the h by 6 is nothing but the kern zone distance, and E is the eccentricity. Now to get that eccentricity here, what is the basic of this design is when we provide the maximum eccentricity, then we require the minimum prestressing force, means minimum number of tendons. So by following that principle, we have calculated the maximum possible eccentricity, that is nothing but h by 2 minus cover, and here we assume the minimum cover for x direction is 30 mm, 30 mm. So h by 6, h is the total depth, 120 divided by 2 is 60, minus cover 30. So we get the eccentricity for this case as 30 mm. And kern zone is h by 6, 120 divided by 6, directly we'll get that answer as 20 mm. Now we are going to use this value of eccentricity and h by 6 for prestressing force calculation in x direction. Now the total moment in middle strip, yes, we already calculated that in step number 4. Here it is 130.275. So we are going to put that value over here, 130.275. So here I have converted that moment. I have converted that moment to Newton mm. So that's why I multiplied by 10 raised to 6. H by 6 is 20, E is 30. And if we do that calculations, we'll get the prestressing force as 2605 kilonewton. Okay, so this is what the prestressing force required in x direction. But we know that we are going to provide this prestressing force in terms of tendons, because we are going to pull that tendons, and every tendon has their limitations. So in the given numerical, whatever tendons are given, they are going to take the load of 100 kilonewton only. So that's why in the next step, that is step number 6, we are going to calculate the number of strands and its spacing in x direction. Okay, so how we get that number? Number of strands is equal to total prestressing force divided by force taken by a single strand, means capacity of a single strand. So the total prestressing force in kilonewtons in x direction is 2605.5, and load taken by the single cable is 100 kilonewton. So this will give us the total number of strand required in x direction, and that after that calculation, that is approximately 26, means 26 number of strands we required in x direction. And where we are going to provide this 26 number of strands? In the middle strip of x. Okay, so to get the spacing of that strand, we are going to use the formula middle strip, total middle strip length divided by number of strands. So total middle strip length is 6.75 divided by 26, and that will give us the answer 0.260 meter. Okay, so this is what the spacing of strands. So here we can comment that what we are going to do is we are going to adopt a spacing of 250 mm, means here we have calculated the number of strands for 1 meter width. Instead of calculating it for the entire, for 1 meter strip, if we adopt the spacing of 250 mm, then the 4 number of cables are there for 1 meter. So this is the diagram in which how we are going to provide that strands. So this is what the ly direction, in ly direction we are providing the strands. So this is for 1 meter width, we have provided 4 number of strands. Okay, and up to the middle strip, in the middle strip we are going to what is the total length of middle strip? 6.75 meter. So in this total distance, we are going to provide total 26 number of strands. Okay, so here I have shown a sample for 1 meter. Got it? Got this diagram? So in the same way, we are going to follow for the y direction. Step number 7 is total prestressing force in y direction. So as you remember, in the design step, in the previous lecture, in the design step, I have used the same number for the step 5, for the step number 7 and 8. I use the same step number, but here I am following the chronological order, so don't get confused over there. It is one and same. So step number 7 is total prestressing force in y direction. Again, first we calculate the eccentricity and h by 6. H by 6 already we have calculated the same value we are going to use, that is 20 mm. But for eccentricity, we assume the cover as 40 mm. So previously what we assumed? Previously we assumed cover as 30 mm. And now for y direction we assumed it as 40 mm. Why this is so? The reason is simple, because these two tendons are going to overlap. Okay, one is going in x direction, another is going in y direction, means definitely they are going to overlap with each other. And to take care of that overlapping, we provided the extra 10 mm. Okay, Then question may arise, why we are not going for the 20 mm, why we used the 40 mm. So the according to means the minimum cover requirement, for the slab we are going to follow is 30 mm. So we cannot go less than that. Okay, so that's why uh, we went higher than that, means 40 mm we used over here in the y direction. So by using this 40 mm cover, the eccentricity is 60 minus 40, that is 20 mm is the eccentricity, and kern zone is again 20 mm. Now let's calculate the prestressing force. Yes, by using the basic theory, moment is equal to force into distance. So if we put the values of total moment in y direction and eccentricity and kern zone, we get the value of prestressing force in y direction as 1361.25 kilonewton. So this is what the total prestressing force required in y direction. So to achieve this kind of prestressing force, we need to provide the tendon, and we know that the capacity of tendon is 100. So let's calculate in the step number 8 the number of strands and their spacing in y direction. So the length of middle strip in y direction is 4.5 meter. So the number of strands in y direction is total prestressing force divided by force of single strand. So total prestressing force we calculated as 1361.25 divided by capacity of single strand is 100. So the total number of strand is approximately 14. Okay, and let's calculate the spacing of it. So this 14 number of strands we are going to provide in the span of 4.5 meter. So that's why spacing between the strand is 4.5 divided by 14, and that will gives us the 0.321 meter. But as we are going to calculate for a 1 meter span, we need to do little bit change over here. Okay, so for that what we are going to do, we are going to adopt a spacing of 320 mm, so that we can provide the 3 cables per meter. So see here how we are going to provide it the cable. So these are the cables in the y direction, so parallel to the ly span. Okay, and this is the 1 meter strip. In 1 meter strip we have provided the 3 number of cables, and for total 4.5 meter middle strip we are going to provide approximately 14 number of strands. So this is for the way in which we are going to provide, or we are going to show the strands in the middle strip. Clear? Now the step number 7. See here, previously step 7 and step 8 means I have repeated the same procedure, and that's why I have given the step number 7, step number 8. So this is what the actual step number 7, or you may continue with the next number, that is this is just number. So step number 9 also you can call to that. Okay, so up to here our design part is finished. Okay, means because already we placed the tendons, okay, in x and y direction. This means design part is done, but whatever design we did, whether it is correct or not, for that we need to take the check. So from step 9 onwards, that check starts. The very first check is the check for the limit state of collapse. Okay, so in this check what we are going to do, in this check we are going to compare the moments. Which moment we are going to compare? We are going to compare the ultimate moment in x direction and ultimate moment of resistance in x direction. So the ultimate moment we get from the formula mu is equal to alpha x wu. See here, but here we used the ultimate load. Previously we used only w, but this is the check for limit state of collapse, so that's why I used wu over here. So alpha x already we get that from the table 26. So 0.089 into 9 into 6 square. So the ultimate moment in x direction we get as 28.836 kilonewton meter per meter. This is for the per meter span. This is what the ultimate moment in x direction, and this moment we are going to compare with the ultimate moment of resistance given in the annexure D of IS 1343 2012, page number 51. So this is the formula in the IS code. MUR, that is moment of ultimate moment of resistance, is equal to FPB into APS into bracket D minus 0.42 XU. Now see here, to get this value of FPB, APS, XU, we are going to follow the table 11. I have taken the so this is the part of IS code. Directly I have taken it from the IS 1343 table 11. See here how we get the value of FPB. So we are going to get the value of FPB from the column number 4, because we are designing for post tensioning, right? So the post tensioning with effective bond. So from column number 4 of table 11 we get the value of FPB, and from column number 6 from column number 6 of table 11 we get the value of XU. XU by D value is there, so we can calculate the value of D, so we get the value of XU. Okay, now but to get this values of column 4 and column 6, first of all we need to get the value, we need to find out the value of column number 2, that is APS into FPU divided by BD/FCK. So here APS is nothing but the area of prestressing steel, FPU is nothing but the ultimate load in the strand, B width, again unit width we are going to consider, that is 1000 mm, D is the effective depth, and FCK is 40. So first of all let's calculate this value of column number 2. So if you do that, APS, first of all area of prestressing, so here we are doing all this for the unit width, so that's why in x direction we have provided 4 number of tendons. Okay, 4 number of tendons each, 4 number of strands, it's strands we have provided 4 number of strands. In each strand we have 4 wires, and area of each wire is pi by 4 into 5 square. So APS, total area of prestressing steel, is 314.159 mm square. This is what the total area. When we put this value of area in this expression, FPU is what the stress, ultimate stress in the steel, prestressing steel. So area steel B, as I told you, we are going to provide the unit width, that is 1000 mm. D effective depth means total depth minus cover, so 90 mm we have, and FCK is 40. So the value of column number 2 by calculation we get as 0.14. Now we are going to check this value in the table. See, 0.14. If we observe this carefully, we don't have any 0.14 value, but we have 0.1 and 0.15, means this row number 3 and row number 4 we need to select to get the value for 0.14 by interpolation. Okay, so for 0.14, 0.1 and 0.15 we are going to select column number 4. See here, don't get confused. This column number 3 is for the pre-tensioning and column number 4 is for the post-tensioning, right? So we are doing designing for the post-tensioning, so we are going to select the column number 4, but for to get the value of this column number 4 we are not going to do the interpolation, because it is very clear that the value for 0.1 is 1 and value for 0.15 it's 1, so directly the value of column number 4, that is FPB divided by 0.87 FPU, is 1. But the same case is not applicable for column number 6. So that's why we need to do the interpolation for column number 6. Okay, so to do that I have used simple table over here. I know that every one of you know how to find out that how to do that interpolation, but those who are getting trouble for calculating the interpolation, they can follow this simple formula, a linear interpolation formula. Okay, so here I have taken the values of column number 2, column number 6, and column number 4 and column number 6. So this is column 4 and this is column 6. Okay, so A2 value directly we can get that as 1, because in between, so we have 1. So here we can use that formula. So B1, B2, B3, A1, A2, A3, X1, X2, X3 we have. So when we put all this value, we get the value of B2 as, if we do that calculation, we get the value of B2 as 0.296, means XU by D value is 0.296, and FPB divided by 0.87 FPU value is 1. Now from these two expressions we are going to use the value of FPB and XU. So how we get that? Means we are going to take this denominator term to the right hand side, so that we get the value of FPB. Okay, so 1 into 0.87 FPU. See here, we have just what I did over here is just I have taken this denominator term to the right. So it is going to multiply with 1. So 1 into 0.87 FPU. FPU is what the ultimate load in the prestressing steel, which is given 1600. And the answer for this value, if we do the calculations, is 1392 Newton per mm square. So this is FPB value, and by using this expression XU by D 0.29, we can get the value of XU. So what is that value of XU? XU is nothing but 38.52 mm. Now we have all unknown values in the expression of ultimate moment of resistance. So when we put all these values in this ultimate moment of resistance formula, we get the ultimate moment of resistance, and that ultimate moment of resistance value is 32.283 kilonewton meter, and which is greater than the ultimate moment. So the moment of resistance, if we observe, this moment of resistance value is greater than the ultimate moment, means we can comment that if MUR is greater than MU, the given section is safe. Okay, hence the section is safe. Okay, so here we complete the step number 8. Now the next check is the check for stresses. In check for stresses, what we are going to do is we are going to find out the compressive stresses, and we are going to compare that total compressive stress developed with allowable compressive stress. Means here we need to find out the stresses first, and then we are going to compare that stress value, compressive stress value, with allowable compressive stress as per the IS requirement. So let's start. So first of all, for this stress calculation, we should know the cable profile. So here we assume that the cable profile is parabolic, having maximum eccentricity at the center and concentric at support. Okay, means parabolic profile, eccentricity is maximum at center and 0 at support, we assumed. And with these assumptions we are going to start for the calculation of stresses. To calculate stress, what we require is the load. So that's why we are going to find out the equivalent load in x direction. See, stress calculation we can do by 3 methods. Okay, already we studied that in the unit number 1. Okay, I provided all that PPTs of stress calculation on the Google Classroom. You just refer that so that it will be more clear to you. Okay, So in that PPTs, what I explained that three methods are there. One is the stress method to find out stress, load balancing method to find out the stresses, and what is the last step, force method to find out the stresses. Okay, so out of that the Sir T.Y. Lean has developed that load balancing method. So from load balancing method, in that method we are calculating the balance load. So that is nothing but the equivalent load we have over here. So the equivalent load according to the cable profile means the cable profile itself is going to minimize the, or it is going to balance the external load. So that is what the importance of the cable profile. And if we have the parabolic cable profile, then the equivalent load magnitude is 8 PE by Lx square. Okay, so that also it is explained in a very neat manner in the PPTs on the Google Classroom. You just follow that. So you just now you just remember this formula, 8 PE by Lx square, equivalent load in x direction. So 8 P is the number of strands provided in unit width, 4 number of strands. Each strand is going to take 100 kilonewton load. Eccentricity is 30 mm converted to meter, and span Lx 6 meter. So the equivalent load magnitude in x direction is 2.667 kilonewton per meter. Okay, in the same fashion, let's calculate the equivalent load in y direction. In y direction we have provided three stands in a 1 meter strip. So only that change is there, and span change, Ly is 9 meter. And if we put all this value in the calculator and do the calculation, we'll get the answer as 0.592 kilonewton per meter. So these are the equivalent stresses, equivalent load we are going to get over here. Okay, now this is what the load developed because of the cable profile. Now whatever unbalanced load or the residual load we have, so that magnitude of residual load or the unbalanced load is total load minus this balancing load. So already we know that the total load is acting in downward direction as UDL is 6. So from this 6 we need to subtract this balancing load. So that's why 6 minus 2.667 minus 0.592. So the total residual load or the actual load remains on the structure is 2.741 kilonewton per meter square. Or if we want to convert that residual load or the actual load present is 0.002741 Newton per mm square, which is acting in downward direction. Suppose if we get this this term in minus sign, then this load is acting in upward direction, right? Means all this this load is acting in upward direction, this load is acting in upward direction, this is also acting in upward direction, and this 6 kilonewton is acting in downward direction. Okay, so the total residual load is 2.741 kilonewton per meter square. This is for the unit area, so that's why meter square unit is there. Now we are going to calculate the moment. Now we are going to calculate the moment for this residual load. We know the formula for the moment, alpha x into q into Lx square. So here what I consider, here I have not considered the W, not considered the value of Wu, but only the balance load acting on the structure, because the cable profile is going to minimize, cable profile is already minimized the external load. So what remain is the 2.741 kilonewton per meter square into Lx is 6, and if we do this calculation we get the answer as 8.782 kilonewton meter. So this is what the moment, and this moment is responsible to develop the stresses. And we know the basic theory, basic bending theory. I during SD2 also I told you that one expression to remember the bending theory formula Elizabeth Rani, may I stress you, from that m by I is equal to stress by y. By using that expression we are going to calculate this stress. So here m divided by I by y, so I by y is z, so m by z expression we have. So m value 8.782 into 10 raised to 6 kilonewton meter is converted to Newton mm, and z value, okay, b into d square divided by 6. So this m by z value gives us the stress, and if we do that calculation we get the value of stress as 3.66 Newton per mm square, which is compressive in nature. Okay. See, compress means if we see the cable profile or the stress profile, these compressive stresses were developed at the top and tensile stresses were developed at the bottom. But if we are designing for the type 1 type of member, then tensile stresses were 0, the magnitude of stress is 0, tensile stress is 0 at the bottom, and at top we get the maximum compression value, that is 3.66 Newton per mm square. So this is what the moment due to the unbalanced load or the residual load. So this one moment we have, and from that moment we get the stress. Now we have the prestressing force, which is again responsible to develop the stresses, and that stresses we are going to call as the direct stress, whose distribution is rectangular. We have seen in the previous lectures, stress distribution diagram for direct stress is rectangular and compressive in nature. So that stress value is P divided by A, 4 number of tendons, so 400 into 10 raised to 3, area 1 meter width, 120 mm depth. So the direct stress magnitude is, if we do the calculation, we get that magnitude as 3.30 Newton per mm square, which is again in compressive nature, and the distribution is rectangular distribution for direct stress and triangular distribution for stresses due to the moment. Got it? Now we calculate the maximum compressive stresses in the concrete at the top by considering both stresses due to the direct load and stresses due to the bending moment. So that is nothing but the addition of these two. So therefore that value is 3.66 plus 3.33, 6.99 MPa or Newton per mm square. Now what comment I have written over here, this is less than the permissible stress of 13 Newton per mm square, hence safe. So see here, whatever total compressive stresses developed is 6.99, and the permissible stresses, from where we get these permissible stresses? We get these permissible stresses from IS 456 2000, table 26, page number 81. Okay, in the below slide I have given that table. So see here, actual stresses are less than the permissible stresses, hence the given structure is safe. Okay, so see here, this is what the table 21, permissible stresses in concrete for we have M40 grade concrete, so permissible stresses in bending is 13 and actual stresses developed is 6.99, hence safe in bending. So here the stress check is also satisfied. Now the last check is the check for deflection. Now in deflection check, what we are going to do here, we are going to find out the magnitude of deflection, and we are going to compare this deflection with maximum allowable deflection given in the IS code. Means what we did for stresses, the same things we are going to do for the deflection. What is the deflection formula? The deflection formula is alpha max is equal to alpha into bracket Q into Lx square, Lx raised to 4 divided by D, where D is the flexural rigidity, Actually we get this deflection formula by referring to the Sir Timoshenko. So he has developed the theory to check that deflection. Okay, so sir has given that alpha max formula, flexural rigidity formula. Okay, so to get this deflection formula, first of all we need all these unknowns. So alpha value is the coefficient directly. This is for the Ly by Lx ratio. If Ly by Lx is 1.5, then the alpha value is 0.00772. Q is nothing but the residual load. Yes, already we have calculated. Lx span is 6 meter. D, so we need to calculate this flexural rigidity, and the formula is EC. Flexural rigidity is equal to multiplication of EC into h cube divided by 12 into bracket 1 minus gamma c square, means this is what the Poisson's ratio square, and we assume that Poisson's ratio is 0.15 for this case. EC value is given, Young's modulus for concrete is given, h is nothing but the total depth we have calculated as 120 mm, and when we put all these data in the flexural rigidity formula, we get the flexural rigidity. So by calculation on calculator, we get the flexural rigidity as 4.658 into 10 raised to 9. Now this flexural rigidity value we are going to put in the deflection formula, and the deflection finally what we get as alpha so by putting all these values, alpha value, q value, l value and d value, we get the deflection as, after calculation we get that deflection value is 5.885 mm. So this is what the actual deflection taking place in the structure. Now we are going to compare this deflection with maximum permissible deflection. What is the maximum permissible deflection? As per the IS 1343/2012 clause 20.3 page number 29 is span divided by 250. Okay, span divided by 250. So span is 6 meter divided by 250. The answer is 24. Okay, so maximum permissible deflection is 24 mm, and our actual deflection according to the Timoshenko formula is 5.885 mm. Hence we can again comment. What comment we can say? What comment we can do? The maximum permissible deflection is greater than the actual deflection, hence the given structure is safe against deflection. And in this way we have taken all the check and our structure is satisfying all the checks, and here we completed the design of two-way post tension slab. Thank you.